Yes, we can see. My request is can you check this, go to the file
Your voice is
and
pretty low actually.
increase the font size so that when we upload to our channel or when we keep it in the content, we can increase it.
Okay, sure.
File preferences, there you can increase the font.
Font size.
No, no, you see in the terminal you have file. No, no, not here, man. Yeah, file. You have edit, go to edit, preference. Click on preferences. Down
Hmm?
extreme, there is a preference. Display, advanced, advanced. Shortcut,
Sorry?
shortcuts. Beside advanced, there is
Your voice is not audible.
beside advanced, there is a shortcuts. Top
E-
drive,
beside?
uh,
Yeah, shortcuts, okay.
yes, okay,
Your
actually,
voice
this,
is breaking.
okay, then zoom out. Go to the edit and click on the zoom out. Cancel this. Cancel. Close it.
Hmm.
Zoom out or zoom in. Try that. Zoom out.
Zoom in is increasing, right?
This address better. Before is better. Keep zoom out. Yeah, that's good. Let's put one more level. Yeah, this is perfect, I guess. Yeah, you can start.
Okay, fine. So today we are going to give a practical hands-on demo how we do things in our cloud, our in our Enomic cloud. So for that, basically we are going to give a basic demo on give a demo on code of basic gates and 2:1 mux and a D flip flop. Uh, today these are the things we are going to explain in our cloud. So to start with, first of all, I'm going to explain a basic NAND gate. A NAND gate is also called as universal gate, as all the other gates and can be designed by using this NAND and NOR gates. So first, to start with, I'm starting. I'm explaining a NAND gate. So, so this is the basic syntax of a Verilog file, which contains module and which contains a module and a module syntax, which means you are encapsulating whatever the design you are writing in the form of a module, and this module will have ports, namely input, output, and in-out ports. Input ports will send the data to the module, and output ports will send the data. Output ports will send the data out, and in-out ports can do the both. And here too we have two input ports, namely A and B, and here we have a one output port, namely C, which namely C. And what we are going to do is uh, we are here we are modeling the NAND gate using uh, gate level. Here we are modeling the NAND gate using structural flow of RTL. Actually, in RTL we can model any design using three types of flows. One is structural flow, another one is data flow modeling, and another one is behavior model. First of all, I'm going to show a demo of NAND gate using structural flow. Here we have taken the Verilog primitive. Here we have taken the Verilog primitive NAND, and we have instantiated a module U1 with inputs as A and B and output as C. As you can see, NAND will have two inputs and one output. And if you see the syntax for structural flow of modeling is any number of inputs can be there, but one output should be there. And if you see the rightmost the leftmost bit will be, the leftmost bit will be the leftmost integer will be the leftmost variable will be the output, and the remaining all will be the inputs. So to test whether our NAND functionality is achieved or not, we will write a test bench. So this is the test bench module which we wrote. This is basically in Verilog, and if you see, we are instantiating the design module whichever we wrote again and connecting with this DB. Basically, what will happen is this DB will sit over the design and it will pass the inputs to the design to check the functionality achieved or not. So here if you see, there is an initial begin block which is a procedural block in Verilog. And if you what is and the main functionality of this initial begin block is it will execute only at the start of the simulation, and it will execute only once. And if you see here, we are passing different values for inputs, and as A and B are two inputs, we will have four combinations. We are passing all the four combinations to check to check the functionality of the net. And then this is the dump file. This is used to dump the waveforms. You, and then we will open this waveform. We will open the waveforms using this dump file in a dump file initial block. And then we have a dollar finish, which is used to stop the simulation after 400 nanoseconds. And coming to the run file, coming to the run file here, if you see, there are two. This is the this is where the bin shell is executed. The bin shell is present, and if you see here, this is where the compiler which are we using is installed. Which the compiler presently we are using is Iverilog, and it is of the 11th version. And then we are using a GTK wave to open the waveforms. So it is installed at this location, and then we are removing the previously dumped waveforms and that for that we are using this rm.out and test.vcd. And then and then this is the command which is used to compile and simulate for the iLog compiler, Iverilog compiler. So for that, what we are doing is Iverilog nan underscore tb.v nan design.v. This is the syntax for which we used to compile and simulate using Iverilog simulator. Then we have this bvp.a.out, which is used to generate the waveforms. And then to open the waveforms, what we will do is we will open the GTK wave using this. As I previously told, waveforms are dumped using this test.vcd into the test.vcd. To open that, what we will do is GTK wave is a command to provoke the GTK wave waveform viewer. So when we invoke this, we can see when we run this script, we can see the waveforms directly as it is completely automated. We are executing all these steps at a single shot. So to execute, what we are doing is, so this is the way to run a shell script. So if you press enter after typing like this, you can see the waveforms directly. So here if you see, when both the inputs are 1, the output is low, and when one input is 0 and another input is 1, the output is 0. So what is the functionality of the NAND is what it is the inverse functionality of the AND gate. So whatever the inputs which are so what will happen with AND gate is when one of the input is zero, the output will be zero. Here, if you see with NAND gate, when one of the input is one of the inputs is one, it will be one. When both the inputs are high, the output will be zero. So the same functionality is reflected here. So if you see when both the inputs are one, the output is zero. And then if you when one input goes low, the output is going high. Similarly here and similarly here. The same is when both the inputs are also zero, the output is going high. So this is the functionality of the NAND. And now we are going to see the NAND functionality in data flow modeling. So this is the data flow modeling. Data flow modeling is done based on the equations which are used to represent the functionality. So here if you see, this is the functionality of the NAND using the equations. So similarly, the test bench file will be the same and the run file will be the same. So if we execute the script again, you can see whether the functionality of the NAND gate is achieved with this data flow modeling or not. So here also, if you can see the same NAND functionality is achieved using data flow modeling. And here if you see, I have used a assign statement, which assign statement is also called as continue. Assign statement is also called as continuous assignments, which means it will evaluate continuously throughout the simulation, and it will assign the values. And if you see, there is something for here we are using equal to, which is called as blocking statement in Verilog, which means until the execution of the statement is done, it will not proceed into the next statement, execution of the next statement. There will be another there will be another అన్న అక్కడ వైఫై ఉంది. ఆ, హలో
Yeah, you are audible, Venkata, but we see here some noises, but it's fine.
now it is fine, right?
Yes.
So this is the data flow. So this is the data flow modeling, and there will be another assignment which we use it to model sequential circuits, which we are gonna see in the next, which we are gonna see in the next demo. I mean next example. In next example in the same demo. So here I am creating another directory to model a mux. Basically, mux is a 2:1. My basically mux is a n is to my basically mux is a n. Basically, mux has n inputs and one output, and a n 2 power log 2 to the base n, and correspondingly n select lines which are used to select uh, this one of the inputs to pass on to the output. So to model and mux, here I am describing the module mux into different types of styles of coding used in Verilog. First is data flow modeling. This is the data flow. This is the data flow module. Here, if you see, and what we are going to do, what we have done is we are assigning C. When S is true, we are assigning the C to A to C. So what this ternary operator does is this is called as ternary operator. When S becomes 1, A will be assigned to A C, and when S becomes 0, B will be assigned to C. Simply in terms of digital terms, when S is high, A will be assigned to C. When S is low, B will be assigned to C. And So here, I'm instantiating the design module. So if you see, so if you see here, so if you see here, when A is 0 and B is 0, S is 0. So what we so so what is the in so as per the design, when S is 0, B is the output. So as you can see, when S is 0, B C is equal to 0. Similarly, when S is equal to 1, A is equal to 0 and B is equal to 1. Since S is true, A will propagate to the output. So that is why C is equal to 0. And similarly, if you see here, when A is equal to 1, B is equal to 0, S is equal to 0. The output here is 0 since C S is the select line is 0. Whatever input which is available at B will propagate to the output. And similarly, when is even both when when S is equal to 0 and B is equal to 1, the input which is available at B1 will go to the C. This is the functionality of a model. So now we are going now we will model this using behavioral behavioral type of problem. So this is called sensitivity list. So this is called always block, which will execute throughout the simulation. And this is called sensitivity list. The sensitivity list will contain all the elements which are required to which are required for whenever there is the sensitivity list. What does the sensitivity list do is whenever there is a change in this within these variables, the always block will go inside and it will execute. It will execute. That is the functionality of the that is the that is why its sensitivity list is created. Here the things to remember is sensitivity list is compulsory, or else you can there is a syntax for Verilog. This is whatever I this double slashes whichever I used is used to add comments, or you can provide sensitivity list in another ways. So the tool will the Verilog has provided a syntax like this such that it will infer the sensitivity list automatically based on the functionality which we have written. This is called data flow modeling.
I think Venkata, you wanted to cover something else also after this Mux and this. I think this should be okay. But if you wanted to show more, that's fine. It's your call.
Okay. So, so the another thing with always block is the left hand side of the always block should be a right. Whereas come previously in the previously shown example here, if you see the left hand side of the always block should be a wire. By default, all the inputs and outputs will be a wire in Verilog. That's why I didn't declare wire here. So the same functionality is replicated here. If you see, whenever S is one, the input and the input A is passed on to the C, which is the output. Similarly, whenever S is 0, the input which is available at B will be passed on to the C. This is the functionality of the mix. So, one more thing in the sense, okay, let's go with FSM. Wait, let me model a D flip flop. So this code is for a D flip flop, which is a sequential circuit, or a sequential circuit in the sense whatever whatever happens in the whatever happens which is respect to a clock will happen with respect to a clock. So here we are having two signals. Here we are having two signals additional with the clock and reset, and there is a data input which is called as D, and the output which is called as Q. So, so to achieve the functionality of the what we will do is so whatever I have written here is in the always block is the always the rate of passage clock and negative visit. Whenever the passage of clock comes, the statements which are under the always block should execute, and whenever the negative reset comes, the statements under the always block should execute. And this is the way of modeling a asynchronous reset. If you remove this negate, it will be you will be more if you will be modeling it. If you remove this completely, you will be modeling a synchronous reset. So here, if you see, whenever the reset is low, we are setting the output to 0, and whenever the reset is whenever the system is out of reset, we are assigning the output to we are assigning the input to output. And here, if you see, we are assigning using a non-blocking assignments. Non-blocking assignment in the sense, in the block, if this if so he in the previously I told for blocking statement, whenever the compiler says a blocking statement, it will stop the execution at that. The execution will not further until the statement is executed. Whereas compared to this, whereas if the compiler encounters the statement, the execution will continue further, uh, even though even though it has a even though the statement is not evaluated completely.
I think with the Venkata, I think it's fine. I think
Okay, fine.
we can cover these topics later. Can we? I think what whatever you wanted to cover this, or it's fine. Basics is a planned agenda for
Okay,
this,
fine.
right?
Yeah.
Yeah. So you can close this, and we will upload this to our YouTube channel.
Okay, fine.
Yeah. Thank you, Venkata. I think I recorded this session. Okay. So thanks. I think let's end for the day.
Okay. Thank you.